Close your eyes and visualize a shoreline, not as it exists today, but as it stood 180 million years ago. The thermodynamics of this world are alien. The sand beneath your feet radiates a heat that feels heavier, denser, the air thick with a humidity that clings to your skin like a second layer. Behind you, there are no oaks, no maples, no grass. Instead, forests of conifers and cycads stretch toward mountain ranges that plate tectonics have not yet eroded into the shapes you know. The silhouette of the horizon is jagged against a sky that holds no birds, only the leathery membranous wings of early pterosaurs. In the water before you, the surface breaks. A neck rises, as long as a telephone pole, topped with a head absurdly small for the creature's massive bulk. It moves with a fluid, hydrostatic grace that defies the square-cube law of biology. When it turns its obsidian eye toward you, you are witnessing an organism that your species will not have the linguistic capacity to name until it has been fossilized in stone for eons. This is the Jurassic. To understand the scale of this era, we must abandon human chronological bias. All of recorded human history, from the first clay tablets of Mesopotamia to the digital device you are holding, fits into a mere 10,000 years. The Jurassic period spanned 56 million years. It is a cavern of time so vast that species arose, conquered continents, and vanished into extinction without ever overlapping with the dinosaurs you see in movies. But this age of giants did not begin with a whimper. It began with an apocalypse. The boundary between the Triassic and the Jurassic, 201 million years ago, is a scar in the geological record, marked not by gradual change, but by a planetary reboot driven by fire. Deep beneath the supercontinent of Pangaea, the Earth's mantle began to churn. A massive upwelling of thermal energy pushed against the crust, tearing the landmass apart. This was the birth of the Central Atlantic Magmatic Province. It was not a singular volcanic eruption, but a flood of basaltic magma that hemorrhaged onto the surface for 600,000 years. The volume of lava was sufficient to bury the entire continental United States under hundreds of meters of molten rock. Yet, lava was not the executioner. The true killer was atmospheric chemistry. The eruptions released over 100,000 gigatons of carbon dioxide, 50 times more than anthropogenic emissions have produced since the Industrial Revolution. This triggered a runaway greenhouse effect, spiking global temperatures by up to 15 degrees Celsius. Simultaneously, sulfur dioxide aerosols choked the stratosphere, creating volcanic winters that froze the planet in between waves of suffocating heat. The oceans acidified. The pH levels dropped so precipitously that the biological machinery required to build calcium carbonate shells failed. Coral reefs collapsed. Ammonites dissolved. On land, the dominant rulers of the Triassic, the Pseudosuchians, the massive, armored, crocodile-line archosaurs that had suppressed the dinosaurs for millions of years, were ecologically deleted. They could not adapt to the thermal whiplash. The world that emerged from the smoke was a graveyard, with 76% of all species extinguished. But in this silence, in this biological vacuum, the dinosaurs found their opportunity. They had survived the heat and the acid, likely due to their smaller size, rapid growth rates, and perhaps a unique respiratory adaptation that would soon allow them to conquer the laws of physics. As the early Jurassic dawned, the survivors began to change. The fragmentation of Pangaea continued, opening the Atlantic Ocean like a fresh wound, creating new humid coastlines and stabilizing the climate into a warm, wet greenhouse state. In this lush, gymnosperm-dominated world, the sauropods began their ascent into gigantism. These long-necked herbivores are the defining image of the Jurassic, but their existence poses a profound biological paradox. How does an animal on land weigh as much as 10 elephants without collapsing under its own gravity? The answer lies in a suite of evolutionary innovations that transformed them into the most efficient biological machines to ever walk the Earth. The first key was their respiratory system. Mammals, like us, utilize a tidal breathing system. We inhale and exhale, mixing fresh oxygen with stale air in a relatively inefficient process. Sauropods, inheriting traits from their dinosaurian ancestors, utilized a unidirectional airflow system similar to modern birds. They possessed rigid lungs connected to a complex network of air sacs that extended throughout their bodies. This meant that with every breath, fresh, oxygen-rich air bathed their lung tissue continuously, both on inhalation and exhalation. They could extract oxygen far more efficiently than any mammal, fueling a metabolism that supported a body mass of 50, 60, or even 70 tons. This pneumatic system had a secondary structural benefit. The air sacs invaded the skeletal structure, hollowing out the vertebrae. A sauropod's neck was not a solid column of heavy bone. It was a marvel of biological engineering, a lattice of struts and hollows filled with air. This reduced the animal's skeletal weight by nearly half without sacrificing structural integrity, allowing them to elongate their necks to suspension bridge proportions. This neck was the ultimate foraging tool, a crane that allowed them to strip vegetation from the canopy across a vast radius without moving their massive bodies. They became titans of efficiency, expending minimal energy to harvest maximum calories. Furthermore, they abandoned the mammalian need to chew. To process enough food to sustain a 50-ton body, a mammal would need to spend every waking hour chewing. Sauropods bypassed this bottleneck entirely. They evolved simple, peg-like teeth designed solely for stripping leaves, which they swallowed whole. Their massive torsos acted as fermentation vats, holding food in the gut for weeks, allowing bacteria to break down the tough plant matter. By outsourcing digestion to their microbiome and eliminating the need for heavy chewing muscles and massive skulls, they could support a small, lightweight head at the end of that impossible neck. This was the biological revolution of the Jurassic. Evolution had unlocked a pathway to gigantism that has never been repeated. By the Middle Jurassic, genera like Brachiosaurus Diplodocus and Apatosaurus had become the undisputed architects of their ecosystem. They were not merely large. They were walking ecosystems, their footsteps shaking the bedrock, their browsing habits shaping the forests. They grew rapidly, depositing bone tissue at rates that stagger modern biology, rushing from tiny hatchlings to invincible adults in a matter of decades. The catastrophe of the Triassic-Jurassic extinction had cleared the board, and the fracturing of the continents had set the stage. Evolution, operating in the vacuum of a recovering world, produced a lineage of animals that pushed vertebrate biology to its absolute theoretical limit. The Earth was no longer a recovering ruin, it was a garden of giants. But as these titans browsed the high canopies, a darker, sharper evolutionary arms race was beginning in the shadows of the ferns and along the shores of the expanding oceans. The herbivores had become fortresses and skyscrapers, and nature was about to forge the weapons necessary to breach them. The age of the peaceful giant was over. The age of the hunter was beginning. Step into the cathedral of the Middle Jurassic. If you were to stand in these forests 165 million years ago, your eyes would register the color green, but your mind would struggle with the architecture of the life around you. There is a profound silence here, missing the hum of bees and the rustle of grass, because neither exists yet. This is a world before flowers. The angiosperms, the flowering plants that define modern agriculture and aesthetics, are tens of millions of years in the future. Instead, you are surrounded by the gymnosperms, the naked seed plants. Conifers tower overhead, their needles waxy and tough, resistant to decay. Cycads, looking like armored pineapples topped with palm fronds, dominate the understory. Ginkgos carpet the ground in fan-shaped leaves that turn brilliant yellow in the dry season. This botanical reality is not just scenery, it is the engine of evolution. Because these plants are fibrous, tough, and low in calories, the herbivores that eat them must become processing plants. The sauropods became fermentation vats on legs. But for the smaller herbivores and the predators that hunted them, this environment dictated a brutal evolutionary logic: adapt or die. This dynamic birthed the most spectacular evolutionary arms race in the history of terrestrial life. Enter the theropods. While the sauropods were conquering gravity, a lineage of bipedal carnivores was perfecting the art of the kill. The archetype of this era, the wolf of the Jurassic, was Allosaurus **. This was not the bone-crushing brute that the Tyrannosaurus ** would eventually become in the Cretaceous. Allosaurus * was an animal built for speed, agility, and surgical violence. An adult measured nearly 9 meters in length and weighed 2 tons, yet it moved with a terrifying lightness. Biomechanically, Allosaurus * is a puzzle. Its bite force was surprisingly modest, weaker than that of a modern lion. How does a predator hunt multi-ton prey with a weak bite? The answer lies in the skull's engineering. The skull of Allosaurus was built like a lattice, light but incredibly strong in vertical compression. Its neck muscles were exceptionally powerful. Paleontologists hypothesize that Allosaurus did not crush prey. It used its head like a hatchet. It would open its jaws to a horrific 90-degree angle, driving its serrated upper teeth downward into the flesh of its victim with the full force of its neck and torso. It was a slash-and-tear predator designed to inflict massive shock and blood loss, stepping back to let the prey weaken before delivering the final blow. But prey species do not go gently into that good night. Evolution is a reactive process, a red queen dynamic where prey must constantly evolve to stay one step ahead of their consumers. As predators became sharper, herbivores became harder. Consider the Stegosaurus. It is an animal so iconic it borders on the cliché, yet the biological reality of this creature is stranger than any fiction. It was a tank, a 5-ton fortress with a brain the size of a lime, yet it was an evolutionary success story. The double row of plates along its back has baffled scientists for a century. Were they armor? Unlikely. They were too brittle and filled with blood vessels. Were they solar panels for thermoregulation? Possibly. But the leading theory today is that they were billboards, massive display structures flushed with blood to signal dominance or attract mates. The tail, however, was no display. At the end of that muscular, flexible tail sat 4 spikes, each a meter long. Scientists call this the thagomizer. It was a weapon of blunt force trauma and sepsis. We know it worked because the fossil record has provided the forensic evidence. An Allosaurus tail vertebra found with a puncture wound that perfectly matches a Stegosaurus spike. The bone had healed around the wound, meaning the predator survived, but it carried the agony of that encounter for the rest of its life. This is not speculation. It is a frozen moment of violence from 150 million years ago, proof that the Jurassic forests were arenas of high-stakes combat. While the titans clashed on land, the oceans were undergoing a transformation arguably even more radical. The breakup of Pangaea had created the Tethys Sea, a warm, shallow tropical ocean that teemed with life. If the land was the domain of the dinosaur, the sea belonged to the marine reptiles. These were not dinosaurs. They were distinct lineages of reptiles that had returned to the water, reversing millions of years of terrestrial evolution to reconquer the deep. The ichthyosaurs were the speed demons of this realm. Through a process called convergent evolution, they had arrived at a body plan nearly identical to modern dolphins and tuna. Physics dictates that to move efficiently through a fluid medium, there is one optimal shape: the torpedo. Ichthyosaurs had streamlined bodies, vertical tail flukes, and dorsal fins. But they were reptiles. They gave birth to live young, tail first, to prevent the newborns from drowning before they could reach the surface for their first breath. Some, like Ophthalmosaurus possessed eyes the size of dinner plates, the largest eyes in vertebrate history. These were adaptations for the abyss, allowing them to dive hundreds of meters into the crushing dark to hunt squid, guided by the faintest bioluminescence. Existing alongside them were the Plesiosaurs the ambush predators. They defied the hydrodynamics of the ichthyosaurs, so evolving a body plan that looks like a snake threaded through the body of a turtle. They swam using 4 massive flippers, a method of underwater flight similar to sea turtles today, but using all 4 limbs in a coordinated rhythm that no modern animal replicates. Their long necks allowed them to strike into schools of fish before their massive bodies were detected, a stealth tactic in the open water. But the apex of this marine food web was the Plesiosaur. Imagine a crocodile's skull magnified to 2 meters in length, attached to a whale's body, powered by flippers the size of garage doors. Genera like Leopleurodon and Plesiosaurus were the leviathans of the Jurassic seas. Their bite force was catastrophic, enough to crush a car. They hunted the other marine reptiles, tearing apart ichthyosaurs and plesiosaurs with a violence that turned the Tethys Sea into a slaughterhouse. The diversity of the Middle and Late Jurassic oceans was staggering. Ammonites with spiral shells filled the water column, ancient cousins of the squid. Enormous schools of fish shimmered in the light, and patrolling the darkness beneath them were reptiles larger than anything that exists in our modern oceans, save for the great whales. This was a world operating at full capacity. The gymnosperm forests were converting sunlight into biomass at an industrial scale. The sauropods were converting that biomass into mountains of flesh. The theropods were harvesting that flesh with hatchet jaws. And in the oceans, life had colonized every depth, from the sunlit reefs to the midnight zones. However, ecosystems are delicate tapestries. The success of the Jurassic fauna was built on the stability of the climate and the specific arrangement of the continents. But the Earth is restless. As the Jurassic period began to wane, the tectonic plates continued their slow, grinding dance. The climate began to shift, becoming more seasonal, more arid in places. The lush, uniform greenhouse was beginning to fracture. And in the undergrowth, beneath the feet of the Allosaurus and the Stegosaurus, two other groups of animals were waiting. They were small, seemingly insignificant, living in the literal shadows of the giants. One group was developing feathers and learning to glide. The other was growing fur and learning to nurse its young. The dinosaurs and marine reptiles were the undisputed masters of the Jurassic, but the seeds of the next era were already sown, or waiting for the wheel of time to turn. The golden age of the Jurassic was reaching its zenith, but evolution is never static. The skies were about to fill with new songs, and the ground was about to tremble with the arrival of a new dynasty. The conquest of the land and sea was absolute, but for millions of years, the sky remained a frontier that vertebrates could not breach. Flight is an expensive evolutionary gamble. It demands a radical reorganization of anatomy, a metabolism capable of generating immense power, and a neural network capable of navigating three-dimensional space at speed. In the Jurassic, the pterosaurs were the first to solve this equation. These were not dinosaurs, nor were they birds. They were a distinct lineage of archosaurs that evolved a solution to gravity that was entirely their own. A pterosaur wing is a marvel of biological engineering. Unlike the feathered wing of a bird or the hand wing of a bat, the pterosaur wing was a complex membrane of skin, muscle, and blood vessels stretched from an enormously elongated fourth finger to the ankle. This was not a passive kite. It was a dynamic living structure reinforced by actinofibrils, structural fibers that prevented the wing from billowing, allowing the animal to adjust its aerodynamic profile in milliseconds. To get airborne, the larger pterosaurs did not run, they pole vaulted. Using their massive forelimbs, they launched themselves quadrupedally, generating enough explosive force to clear the ground before their wings snapped open to catch the updrafts. They filled the Jurassic skies with a diversity that ranged from the sparrow-sized to the airplane-sized, casting shadows over a world they had mastered. But in the late Jurassic, in the tropical lagoons of what is now Germany, the pterosaurs were joined by a ghost in the evolutionary machine. The Solnhofen limestone, a geological formation famous for its exquisite preservation, has yielded a fossil that fundamentally altered our understanding of life history. Archaeopteryx **. Here was an animal caught in the act of becoming. It possessed the teeth, bony tail, and claws of a theropod dinosaur, yet it bore the unmistakable asymmetrical flight feathers of a bird. Archaeopteryx * is the physical embodiment of a transition, a creature straddling the line between the reptilian past and the avian future. It proves that the sky was not conquered once, but twice, by different lineages finding different solutions to the same problem. Every sparrow on your windowsill today is a direct descendant of these Jurassic experiments, a living dinosaur that survived by mastering the air. While the archosaurs dominated the sunlight, another revolution was taking place in the dark. The Jurassic mammals were small, rarely larger than a squirrel, living in the literal and figurative shadows of the dinosaurs. But their size was a strategic adaptation, not a failure. In a world ruled by visual predators, the safest place to be was the night. To survive in the dark, mammals evolved a suite of sensory superpowers. They developed a three-bone middle ear structure that granted them acute hearing, capable of detecting the snap of a twig or the rustle of an insect in pitch blackness. They evolved fur for insulation, allowing them to maintain high body temperatures when the sun went down. This warm-blooded metabolism was a double-edged sword. It allowed for nocturnal activity, but it required a constant intake of calories. These early mammals were metabolic furnaces, driven by an insatiable hunger for insects and worms. They were the underdogs of the Mesozoic, surviving by occupying the niches that the dinosaurs ignored. They played the longest game in evolutionary history, waiting 160 million years for the asteroid that would finally clear the board. You are here today because they survived the Jurassic night. To reconstruct this world, we rely on three great windows into the past: geological formations that serve as time capsules of the late Jurassic. In North America, the Morrison Formation preserves a harsh, semi-arid environment of seasonal droughts and flash floods. It is a graveyard of giants, where the bones of Allosaurus, and Diplodocus are found piled together in ancient river channels, evidence of catastrophic die-offs where water became a trap. It tells a story of a dynamic, dangerous landscape where survival was a constant struggle against the elements. Across the Atlantic, the Solnhofen limestone of Bavaria offers a different view. Here, in quiet hypersaline lagoons, the water was so stagnant and devoid of oxygen that dead animals did not decay. Soft tissues, delicate wing membranes, and the fine barbs of feathers were preserved in limestone, as smooth as lithographic plates. Solnhofen gives us the resolution that the Morrison lacks, showing us the delicate, fragile beauty of the Jurassic ecosystem. Further south in Tanzania, the Tendaguru Formation reveals the African context. Here, the giants were different but familiar. Giraffatitan**, a close relative of the North American Brachiosaurus**, reached its head into the canopy, while the spiked Kentrosaurus** browsed the understory. The similarities between the faunas of North America and Africa tell us that while Pangaea was breaking apart, the continents were not yet fully isolated. The world was fracturing, but the pulse of life remained synchronized across the widening oceans. As the Jurassic period drew to a close, 145 million years ago, there was no sudden cataclysm. The transition to the Cretaceous was a slow fade. The climate began to cool slightly, the continents drifted further apart, and the floral revolution of flowering plants was just on the horizon. The famous Jurassic lineages, the stegosaurs, the megalosaurs, began to decline, replaced by the ancestors of the tyrannosaurs and the horned dinosaurs. But the legacy of the Jurassic is not buried in the past. It is woven into the fabric of the present. The oil that powers your civilization is, in many cases, the distilled essence of Jurassic plankton. The birds that sing outside your window are the direct heirs of the theropods that hunted in the gymnosperm forests. The mammals that dominate the modern planet are the descendants of the furry insectivores that scurried beneath the feet of the giants. The Jurassic lasted for 56 million years. To put that in perspective, human civilization has existed for less than 10,000. We are a blink of an eye in the history of this planet. The Jurassic was an age of stability and success, a time when life pushed the boundaries of size and physiology to limits that have never been approached since. It teaches us that the Earth is resilient, that life is plastic, and that dominance is temporary. The giants are gone, their bones turned to stone, but the forces that shaped them, evolution, tectonics, climate, are still at work. We walk on the same stage, merely in a different act of the same play. The Jurassic is not just a chapter in a textbook. It is a reminder of the deep, majestic time that flows through our world, a testament to the wonders that evolution can craft given enough time and space. As you close your eyes and let the image of the shoreline fade, remember that you are part of this continuity, a traveler in the same epic story that began on those warm, ancient sands.